You know that screen you're looking at right now? It isn't just a window. It's a triumph of applied physics, turning invisible waves and streams of electrons into a living, breathing picture. So today, we're going to pull back the curtain and uncover the incredible science that makes television possible.
And this quote, wow, it just perfectly sets the stage for what we're about to dive into. This really is the story of how humanity tackled one of the most audacious challenges you can imagine, teaching the laws of physics how to see across huge distances. So what was this impossible problem? Well, at its core, it was this. How do you capture an entire scene, all of its light, all of its motion, and send it somewhere else instantly? I mean, you can't just teleport a picture, right? What feels instantaneous to us is actually a super clever, high-speed illusion. To pull off this illusion, the early inventors realized they basically had to deconstruct reality. The whole process boils down to these 4 steps. First, you have to break an image up into tiny little pieces. Then, you convert the light from each of those pieces into an electrical signal. Third, you send all those signals, one after another, in a super fast sequence. And finally, you put them all back together so quickly that our brain sees it as one single moving image. And this is the wild part. The final crucial piece of the puzzle isn't in the machine, it's in our own biology. It's a phenomenon called persistence of vision. See, our brains actually hold on to an image for a tiny fraction of a second after it's gone. So if you flash enough new pictures or frames in front of our eyes per second, our brain just gets tricked and smooths it all together into motion. A TV isn't really showing you movement. It's showing you still pictures so fast, your brain creates the movement for you.
Okay, so they had the theory, but how did they actually do it? Well, the first attempts were these incredible marvels of mechanical engineering before making the jump from clunky gears to something much, much faster, pure electrons.
All right, say hello to the Nipkow disk. This was the brilliant first step. It was literally a spinning disk with holes punched in a spiral. As it spun, each hole would scan one horizontal line of an image, letting light hit a special cell behind it. More light, stronger electrical signal. And it worked. Kinda. But it had a fatal flaw, one rooted in basic physics. Inertia. You just can't spin a physical disk fast enough to create a detailed, high-resolution picture without the whole thing flying apart.
And this comparison right here shows you exactly why they had to make a huge leap. On one side, you've got mechanical scanning, physically limited by how fast you can spin a chunk of metal, but on the other, you have electron beams. These things have basically no mass, and you can steer them with magnetic fields, something called the Lorentz force, and nearly the speed of light. The solution wasn't better engineering, it was a whole new kind of physics.
So here's the key takeaway. To move faster than spinning metal, inventors had to go smaller, a lot smaller. They had to harness the electron and play by the weird, wonderful rules of the quantum world. And this led to the invention that defined television for more than half a century, the cathode ray tube.
So how did this amazing device actually work? Well, inside a big glass vacuum tube, a heater literally boils electrons off a little piece of metal. Then, a huge voltage shoots them forward like an electron cannon. Powerful electromagnets steer this invisible beam, making it scan across the screen, line by line, just like your eyes reading a page. They call that raster scanning. And when those electrons slam into the screen, which is coated in phosphor, they make it glow. They were literally painting with electrons.
Okay, so we've got a black and white moving picture. That is incredible. But of course, the story doesn't end there. The next challenges were just as huge. How do you add realistic color? And how do you make sure every single TV in the country is painting the exact same line at the exact same time?
The solution they came up with for color is just ingenious, mainly because it doesn't even try to recreate every color imaginable. Instead, it cleverly exploits our own biology. See, our eyes have 3 main types of color-detecting cells, called cones, that are sensitive to red, green, and blue. So color TVs just put tiny little dots of red, green, and blue phosphors on the screen. By zapping those dots with different intensities, it tricks your brain into mixing those 3 colors to see the entire spectrum.
And here's another super smart engineering hack. Engineers figured out that our eyes are way more sensitive to changes in brightness than they are to changes in color. So, to save a ton of broadcast bandwidth, they split the TV signal into 2 parts, a high-detail brightness signal called luminance and a lower-detail color signal called chrominance. It was just a really efficient way to do things.
So you've got this complex signal flying through the air as an electromagnetic wave. How does your TV even catch it? Well, that's where your antenna, just a simple piece of metal, does something that feels like magic. As that invisible wave washes over the antenna, its changing magnetic field creates a tiny electrical current in the metal. That's Faraday's law of induction right there, turning an invisible wave back into the electricity that paints your picture.
Now, for decades, this analog system of waves, it worked, mostly. But you know how it was, right? Any little bit of interference, a storm, a car driving by, could mess with the signal, giving you static and ghosting. The signal was fragile. The next great revolution wasn't just an improvement, it was a total game changer, moving from those noisy, imprecise waves to perfect, clean digital bits. The difference here is fundamental. Think of it like this. An analog signal is like a photocopy of a photocopy. Every time you copy it, it gets a little worse, a little fuzzier. Static just gets mixed right in. But a digital signal isn't a copy, it's the original recipe. It's just a list of numbers, zeros and ones. You can copy it 1,000,000 times, and it is perfect every single time. And if some of the data gets lost, error correction can often just rebuild it from scratch.
And just like that, everything, the brightness, the color, the sound, all of it gets converted into this new, powerful language. Just a long, long stream of simple binary code. Clean, perfect, and you can reproduce it endlessly.
This whole digital revolution also paved the way for totally new kinds of screens. We finally moved away from firing electrons inside a giant vacuum tube to controlling light at the molecular level with the amazing flat screens we all use today.
So the two main technologies you see today are LCD and OLED, and they could not be more different. An LCD screen is basically like 1,000,000 tiny window shutters. There's a big backlight, and little liquid crystals twist to either block that light or let it pass through. But an OLED screen is completely different. Every single pixel is its own tiny light bulb, made of an organic molecule that glows when you give it electricity. And that's why OLEDs can have perfect deep blacks. To make a pixel black, you just turn it off. And to give you an idea of the scale we're talking about here, a modern 4K screen has over 8 million of these pixels. And your TV's processor is controlling the brightness and color of every single one of them 60 or even 120 times every single second. It's just mind-boggling.
So when you step back and look at the whole story, it's just an incredible journey. From the mechanical whirring of a spinning disk to the quantum leap of electrons in a glass tube, all the way to the solid-state physics of individual glowing molecules. This quote really nails it. Television is the ultimate proof that science can take an impossible dream and make it a visible reality for all of us.
Which of course leaves us with one last question to chew on. We've come this far, from gears to electrons to molecules. So what's next? What new kind of physics is going to power the screens of tomorrow? That's a story that's still being written.